so the response spectra, the concept of the response spectra, I need to explain it a little bit. So as I have explained it to you lastly, that that we are calculating the over the time of the ground motion, you calculate the the building response, which is called U, and for the entire time, and then we for a particular frequency and particular damping. Let's see this thing. It's called, we call it as the zeta. This is the damping, right? So this is the damping, and that is basically the H, right? Earlier I was showing it as the H. So this is your damping part. So you calculate the maximum value, and that will be your peak value of this one, right? So that is your U0. When you can calculate your U from there, right? Now, if you calculate the U dot, then you can calculate the maximum of U dot. So it is a peak value of U0, right? And then if you can calculate U double dot, then that is equals to your, okay. So you have a ground acceleration. This is your ground acceleration. You put it as an input and calculate. So this is your UG double dot T. So this is your ground acceleration, right? So this is your ground acceleration, and that ground acceleration, you input it to the system and you calculate UT, right? So that you calculate your UT, and this is your system response, and you calculate the maximum value, then that will be your this values, right? U0T. Then you can calculate you can differentiate that and use the ground, making it the velocity, and then calculate your U0T. Then making it an acceleration, you can calculate U0T. So these are the deformation spectrum is a plot of U0 against T or your N, right? So that's your this thing. And U0 dot is called the relative velocity response spectra. So U0 dot, if you can calculate, it is a relative velocity response spectra. And U0 double dot, then it will be the acceleration response spectra, right? So these are the three things you can calculate, right? Now, deformation response spectra, if you can plot it with your the time period, if you are plotting it with a time period or the period of the motions, right? So then it might be looks like this way. So please see that the peak deformation is equals to 0 when the T equals to 0, right? So that's equals to 0 when Tn equals to 0, then it is basically a very stiff structure. I told you that this side will be the stiff if it is a time period, and this side it will be the flexible form, right? So if it is a stiff structure, then it will not expect to move at all. So there will be the spectral displacement will be equals to 0, right? And if the Tn is going towards this side, so that means Tn is more, then the Tn basically, Tn is equals to 2 pi by omega n. So 2 pi by omega n is equals to omega n is equals to root over of k by m. So that means this will be the 2 pi root over m by k, right? So so the Tn is large, means, or the Tn is infinity. So Tn is infinity means m is infinity. So that means it's a very large mass, or the k or the stiffness is basically the 0. Then the Tn will be infinity. So for such a system, the mass is mass remains stationary when the ground underneath it moves, right? So that is the picture where we have seen, showing you that this is the case, right? So the ground moves, the mass remains stationary. So in that case, it will be like this. So if the Tn becomes large, if the T becomes large, then this PGD, this D value, whatever is the D value, this is actually equals to peak ground displacement. So that means peak ground deformation response will be 0 for T is basically 0. Then this is 0. And if the T is large, then basically these things will be a constant value. And if you can see that constant value, that will be equals to the peak ground displacement. So that becomes the peak ground displacement. So if you can calculate from your time history the peak ground displacement value, and then you plot the deformation spectrum, you will be seeing that numbers matches with them, because this thing will be asymptote to this peak ground values. Okay, so let's see the pseudo velocity response. So this peak value of the strain energy, how much is the strain produced, that is your E, we call it as the ES0. So ES0 means it's the elastic strain at the peak value. So 0 indicate the peak value. So it is a half K into D square. So that means that half M into half K into X square is the half K into X square is basically the spring energy, right? So that half K into D square, if you can calculate, so half K equals to this is equals to 2 pi by M by omega N. So K, omega N equals to K by M, root over. So basically, this will be equals to M by Tn by 2 pi into D. So that D will be equals to the omega into D square. So that is equals to D square values. So if we can put that, then V is equals to omega N into D. I told you that therefore the pseudo-spectral velocity V will be equals to omega N into D. So this will be equals to 2 pi into Tn into D. So that will be equals to 2 pi Tn into D, means it's basically the U0. So therefore, if you plot your V versus Tn graph, so that means your pseudo response versus the Tn graph, then you can see here these pictures will be like this. Now, so that means at your zero time period, the X is the SD equals to 0. So that means this will be also 0. So V0 means for the Tn, at Tn, this will be also 0. But at the Tn equals to infinity, since it's at the 0 period, the system is so stiff that it does not deform. So hence it does not store any energy, and therefore that infinite system is so flexible that its spring lacks any stiffness to store the strain energy too. So that means because at the high frequency or the high time period, it will be also becomes as 0. So the pictures will be always, a V picture will be always like this. Okay, so it starts from 0, this one. But the displacement spectra will be always like this, right? So that is your two difference of the velocity spectrum, right? Anybody has any question? Okay. So you understood these conversions, right? So because this is your K, so K equals to M into omega N square. So that M, I will take it out, and omega N square means 2 pi Dn. and D, so that I can put it here. So that way we explain this part. Now, the pseudo acceleration response spectra is the A value. A equals to, therefore, the omega n square into D. So D, if it is a deformation spectra you have calculated, then this will be equals to 2 pi by Tn into D. So that will be equals to the pseudo acceleration response spectra. And this pseudo acceleration response spectra will be this A has a unit of basically the unit of acceleration, right? Acceleration, because this is your D into D is the response, and then there will be Tn means 1 by second. So, and then 1 by second square. So it's the meter per second square. So it will be basically the response spectrum of this one. Now, so if this is a building, or this is this one, but there is a UG, or the ground motion, and then there is a U. So that means this will be the K into U is basically the spring force. And that spring force, if it's tried to move it here, this has to be balanced by the velocity at the shear at the base. So this is a VB, right? So this VB0 is basically so this is your static force. We call it as a static force. So this is your static force is Fs. So this is equals to K into U. So the static force peak value will be equals to K into U0's peak value. So that will be equals to V into P0. And V into B0 is the base shear. So that will be equals to mass into acceleration. So mass equals to W divided by G into A. Now, so if you plot this one, so at low period, that means at the zero period, whatever is the acceleration you get, so that acceleration is basically equals to your PGA. So at the Tn equals to 0, or the time period 0, or the 0 time period, whatever the spectral response or whatever the pseudo acceleration response, that will be equals to basically the peak ground accelerations, right? So it starts with the peak ground acceleration, and as it goes to the high frequency, it becomes gradually 0, right? So these are the three things you should keep it in mind the same. So that means at the low period, both the velocity and the displacement response spectra should be 0, and at the high period, the velocity response spectra is also 0, and but at the high period, the velocity response spectrum is 0, but the displacement response spectrum, or SD, is equals to PGD. And at the low period, at the 0 period, whatever value you are getting it, that will be in the acceleration spectrum, that will be equals to your peak ground acceleration values, right? So this response, we need to compute for any structures, right? But the problem is this, that you do not know the omega n values, right? Or the structures omega n, you do not know. So what you do is actually, as I can see it, I'm going to show it to you, that this is your time period. So this is your time period of the building, right? But the building period you may or may not know. So, but whatever is the ground motion, you calculate this response spectrum, and then if you know your building values, or the omega n values, then you can calculate that for that earthquake, what should be the acceleration spectrum is expected, right? So that you can do it in a reverse way. So that means for your for your ground acceleration, you first calculate the response for a different period. Your building will be a particular period, so that value you know. So if you know that value, so then you can calculate what will be the response spectrum value or the SA value or SD value or SV value, PSV value. You can all calculate based on that. Okay, so that's the things we need to first do. Okay, next part is this, that all the engineers and the seismologists always try to plot this response spectrum in a tripartite plot, right? So a tripartite plot is just looks like this. Okay, so this is your okay. So let me do this one. So if you can see it here, that so P equals to 2 pi by Tn, or the omega n into D, right? So this is your omega n into D. So if you know the D value, you can just multiply with the omega, you will get the P value or the velocity response spectrum, right? So D, if you know, you can calculate V by multiplying it with the omega. So this is V equals to omega n into D. And then if you know if you know V, then you can calculate 2 pi by Tn, then this will be into V, right? So or you can say that A into Tn divided by 2 pi, A into Tn divided by 2 pi will be equals to V, and then V equals to 2 pi by omega n into D, right? So that's the relation. So how V is in between. So it is a 2 pi by omega n into D is the V value, and A will be equals to 2 pi by Tn. So just we keep the V as the same, and then we have written it like this way, right? So if you take the log of this expression, so log A plus log Tn minus log 2 pi will be equals to log V, right? And will be equals to also log 2 pi minus log Tn plus log D, right? So that's the relation from here, right? So this is one equation. If you can see it, this is one set of equation with a V, and this is another set of equation with V. So there are two sets of equation with V. So let V becomes the y-axis. If V is the y-axis, then this will be equals to log, and this is your x-axis. These two values are x-axis values, right? So this is log 10. So then the y and x, and this is your A, and this will be the minus values, right? So if you can see this plot, then you can see that our on this side I plot the Tn. On this side I plot the Tn, and on this side I plot the V, right? So that this is the PSV or the V, whatever you call it. This is the pseudo things. And so if you can plot this one versus so then this is basically what we can plot it by this axis, right? So these are the V and this one. Okay? Now we also plot the acceleration, and the acceleration values are 45 degree with the Tn axis, right? So this is this will be the 100 and minus 135, because this is the minus values. So therefore these numbers are basically these things are basically the acceleration things, right? So these are the Tn with the different acceleration values, right? So you are basically plotting the PSV versus Tn, and if you can make this tripartite plot, so this axis will be the all the acceleration values, and since this is the plus, so this is the 45-degree, it will be the d-axis, right? So this is your d versus t, and this will be the a versus t, right? So this is the d versus t, this is the a versus t. Now you need not to plot all the three values. You only plot the v and t, right? So the v values and t values, that response, you will be plotting it, and then it will be seeing that it will be meeting at this point. So that will be your t0 values, and this value, whatever you are getting it here, that will be the peak acceleration, and then this will be the at the point where so this will be the peak acceleration, and this will be the peak displacement. And if you plot these two values, it's just like this, then this will be the peak ground velocity, right? So what will be the peak ground velocity you can calculate, and the peak ground displacement you can calculate, and so that means, because it becomes a totally constant at this point, so this point will be the peak ground displacement value, and you can read it from this graph. So from this graph, you can read what will be the peak ground displacement values, and from this graph, as it reaches here, you can find out what will be the peak ground acceleration values. So peak ground deformation is read with a 45-degree from here, and this is read with a 135-degree from. Does it make sense? The tripartite plot. So you calculate PGV versus Tn and plot that values, and then in the tripartite graph, this will be automatically, you will see that what will be the PGD and PGD values you can calculate it, because these are only the axes. So from that axis, you can read the values, right? Okay. So, so this response spectra that shows the maximum horizontal response is basically the interest to the engineers, and the seismologists are interested to calculate the horizontal response spectrum, particularly the horizontal response spectrum, to compute all the earthquake hazard and all these things based on the horizontal response spectrum value. So all our prediction equation, or the ground motion prediction equation currently we use for the earthquake hazard, these are all spectral acceleration values, right? So we need to calculate the spectral acceleration value very clearly. Okay. So okay. So you have understood how to calculate these things, right? And the response spectrum, how do you calculate that? So in MATLAB, there is a code function, or there is a code, it is called convolve, right? So this is a CONV. You can use that. So what you need to do is to take the time history, and that time history value is your UG, and give the time history value, and also you have to give this value. Okay, so e to the power, your damping value will be known, or the damping or H value will be known, and then omega n and this one, and this will on the other side of the function. So because the convolution is always with a two signal, right? So this is equals to f convolution of G, right? So this is equals to your, your output when it will be equals to sums H convolution of G, right? So that you can calculate. And so this is basically done in a MATLAB as a convolve. You have to give F function and you have to give G function. Now F function is in this case is my acceleration values, and the G function will be equals to this number, e to the power j omega n t into sine into this part. So please remember this is omega d. So omega d means it's omega n into 1 minus. So omega d will be equals to omega n into 1 minus of damping square, right? So that you have to put it here, and this will be equals to omega d 1 by omega d, and these you do not forget this is the minus sign. So that if you can do this convolution, then that will be giving you all the ut values, because as I give the this 1/2 and minus half and these things, they give me an output. So this will be also given me an output, right? So that will be our ut values, right? Now, if you do the differentiation of this ut, then it will be u dot t, right? So if you do a differentiation of this one will be equals to, then if I differentiate this one, then it is a xi of omega n into ut minus of this part, right? So because this is these functions will be differentiated, and then so this is the e to the power minus m into x. So if you do it, so then it will be m will be coming outside e to the power mx. So that will be this part, and the next it will be the cosine part. The sine becomes the cosine thing. So that is equals to u dot t. So u dot t, and then if you can do again, then that will be the u double dot t. But you need not to do u double dot t, because u double dot t will be always equals to this one. So if you already know the ut and you already know the u double dot u dot t, you can calculate u double dot t, right? So that's your things. So we can calculate the relative velocity spectrum, acceleration spectrum, the plot of u0t and u0 double t. So peak values of these things you can calculate as a function of Tn, right? So pseudo velocity and this response you can calculate. Now, so two things. One, you need to understand the pseudo velocity and relative velocity spectrum. So these are the two different things, so that you need to understand. So this is the pseudo velocity and the relative velocity part. So if you can see that, so this for a particular earthquake, you will be seeing in the low velocity, low frequencies, a low time period side, they are more or less the same, right? So there is nothing big variations. But after a certain frequency or a certain time period, you will be seeing that with at the high time period part, they will be different, right? So this is basically the relative velocity things, and this will be the pseudo. So this will be basically the omega n square into d. So this back, and this will be equals to u double dot t maximum values of that, right? So that's your two different functions, and so if the v is the velocity, pseudo velocity is response is less than u0, that means the peak ground velocity. So this u dot 0 is the peak ground velocity, right? If this is the less than this peak ground velocity, this is peak. This is the peak. This is the peak building or the peak response velocity. Okay, peak peak response and peak velocity response. Peak velocity response. If D is this one, then and the difference between them two are large. Since the Tn is infinity, D becomes this one, U0 becomes UG0, and if, as the D is UG0 means the P tends to 0. And when the T is 0, that means on this side, the short period system V exceeds this one, and this will be more or less the same. Right? So pseudo velocity and the pseudo damping you can calculate and see this one. And similarly, if your U double dot T, that means the building acceleration equals to omega n square into T part, and this U0T will be equals to the peak value of this one. So that means peak value to multiply the omega n square will be equals to the acceleration spectrum, and that is your A values. So A values, if the damping is present, then U double dot T will be equals to this damping part will be involved here, right? So this part will be the same as this omega 0 A, but U double dot T, and if there is a damping is significant, then these two are different values, right? So then that will be shown at a high frequency side. There will be a little bit difference between the acceleration response spectrum and the pseudo response spectrum. So does it make sense? So that means if you have a the acceleration record, you can calculate all the parameters you wanted by using this particular relations. Now, this is basically a convolution operation. So you do the convolution first and compute the deformation or the maximum values of U, and then by using that Duhamel integral, and then from there you can compute the differentiation and integrations of all the things, and it will be actually multiplication with your omega n. Then you can calculate your velocity response spectra or the pseudo velocity response spectra, and multiply with again omega n. You can calculate the pseudo acceleration spectrum or PSA. But if you need to calculate SA or the relative velocity things, then you have to differentiate your U double dot T and U dot T and calculate that numbers, right? So then you have to calculate these numbers to compute the U dot T part. So you have to use this part. So this is again the convolution. This is again the convolution, but this convolution is with the cosine term, and this and then minus of this part is present, so that you can calculate U dot T, and then you can calculate your U dot T's peak values. Okay, so hopefully this will be giving you some insight for how to calculate the response spectrum. So the response spectra, we always, the engineers, they need the response spectra for the building response calculation, and that will be helpful for understanding what frequency provide what type of response for a ground, and what will be the building peak frequency values, so that they need to establish by studying these things, and they can design it based on that. Okay, based on that informations. So after the response spectra calculation, our next target is to calculate the Fourier transform. Okay, as I told you that we can represent a function versus either by time or by frequency, and or by the position in meters or by the inverse of the wavelength, but in case of your time series analysis, this is the time and frequency we are interested in, right? So, so there are two domains. One is the time domain, and other is the frequency domain, and we have to transfer between these two domains, right? So there is a time domain, and is basically the recorded data, and we have to convert it into the frequency domain. Then it will be time to frequency domain. Then we call it as a Fourier transform, and from the frequency domain to time domain, we call it as an inverse Fourier transform, right? So, so the time domain to frequency domain conversion is called a Fourier transform, or from the spatial domain to the frequency domain. If it is the data collected over a space, say suppose if you have collected the gravity data or something like that, so then it can be converted into the frequency domain. So the time to frequency, or the spatial distance to the frequency, these are all Fourier transform. Now, what is a Fourier? So Fourier is a mathematicians, and he has established this type of transform theory. So everything is on his name. It's a Fourier transform. And so we all know that our time series data, or might be the any gravity data, magnetic data, or these things are all some sort of a sinusoidal or cosinusoidal functions, just like this one, right? So now this function, whatever we are seeing it here, this function is a superposition of various frequencies having various amplitude. So they are all together, and if you can add all the frequencies and this one, then you can add it and then summed over, then that will be a complex or some data, and that data will contain different frequencies having different amplitude. So if you take the Fourier transform of that the which frequency has what type of amplitude, or how much will be the amplitude, that it can separate. Okay. So just like this one, say suppose there is a frequency 2, frequency 3, frequency 5. If you can have with the different frequency values, and then you add them together, then that will be the total, which will be this one. So that will be the total functions, what it looks like. But these functions all contain the different frequencies, right? Now, if you take the Fourier transform of this one, then ideally you should get, if your all other all other settings is okay, then you will be seeing a one's peak here, another peak here, another peak here. So there will be some peak, but depending upon the problem with your data sampling and all these things, you might miss one or two peak because you might not have been done the sampling correctly, but you can see all the peak values in this one, right? So we all know this Fourier transform is basically a complex representations, right? So you all know that the Fourier, whenever you take the Fourier transform, it is basically it will be a complex spectra will be provided to you, right? So the complex spectra means it has a real part as well as a imaginary part. So if you can see that real part and imaginary part, so this is your A is the real part amplitude, and B is the imaginary part amplitude. So this is a complex spectrum Z will be equals to magnitude of G into e to the power of j theta. Now this e to the power of j theta is basically or e to the power of I theta, whatever you can call it. So that will be always cos theta plus I sin theta, where I equals to square root of -1, and Z is the square root of a square plus b square. So it is a square root of the real part amplitude and the imaginary part amplitude. So if you can do that, then the phase means is a arctan of B by A. So that means the coefficient of the imaginary part divided by the real part, right? And the conjugate is this one. So e to the power. So if I write it down, so then it is the cos 2 pi f into t plus I of sine 2 pi f t. So then this will be equals to e to the power 2 pi ft, I 2 pi ft. So this is your complex number. So this can be written as a cos 2 pi ft is the real part, and the sine 2 pi ft is the imaginary part, right? Means sine 2 pi ft is the imaginary part. So this will be a pictures like this, and the frequency from the peak to peak, if you can calculate, then that will be equals to your time period. So time period means it's a 1 by frequency, right? So 1 by f. So that distance will be equals to 1 by f, right? So 1 by f is the wavelength, and this frequency is f. Okay, now the Fourier transform comes from basically from the Fourier series, which might be you have done in case of your so while you have used your Fourier series. This is the trick every takes. Yeah, that will put it on first. But in the being, finally, in your physics, but whenever you do it with your string, you things of the flash seal, not the ghost seal, when that time you have used all the Fourier's when the calculations, right? And also the heat conduction with equation, being the Fourier series. So the Fourier series is basically an exponential format, and then they have a 0 by 2 is the constant part, and then there are two binary cosine form, because as far the Fourier that any to complex things in a space as the series of a sine and a cosine, and that we have a constant part, and then that will be equals to the Cn into this part, and this Cn is the amplitude part, and this amplitude is equals to 2 pi n by 1 by 2 pi. If you integrate from the minus t to plus t, then it will be the I pi by t into n into ft, right? So that if you need to calculate Cn from here, you can use that ft values and you can compute that, right? So this is your omega n. So this omega n is the frequency, as I said. So then n equals to pi by t, and then delta omega is basically pi over the t. T is the time period of this one. So if you can put that, then if this one in terms of t, then 1 by 2 pi into all the numbers, you can put it here, and then you can get that the main part is this, that f omega will be equals to this one, and f prime of f omega will be equals to 1 by 2 pi. So f, the Fourier transform, f omega will be equals to minus infinity to plus infinity into e to the power I minus I omega into t into ft of dt. So this is your Fourier transform part and inverse Fourier transform of your f of t will be equals to 1 by 2 pi into minus infinity to plus infinity e to the power I omega t into the f omega d omega, right? So these are forms of Fourier transform pairs. Does it make sense or not? You have all used that, right, in your digital signal processing class or anything. So that's the part. So any signal G, if you can say that this will be, if you take the Fourier transform. So if I take a signal GT and take the Fourier transform of that signal, I can say that, okay, this is the Fourier transform of GT. If I try to calculate, then it will be giving you a function which is called, so the whatever they will be giving you is a complex function, right? It's a complex function. So complex function means it has a real part and it has a imaginary part, right? So if you try to calculate your amplitude spectrum of the Fourier transform, then you have to say that amplitude spectrum will be equals to the whatever the real part, the square and the absolute and the imaginary part square, then that will be equals to the amplitude spectrum of this one. Okay, or the magnitude spectrum or whatever is that. So if the GT is basically the acceleration, then whatever the FGT will be, or the Fourier transform of GT becomes what? What will be the unit? If I take the Fourier transform of a acceleration data, then whatever I get is the spectrum, acceleration spectrum, right? Now, what will be the acceleration spectrum unit use? What is the acceleration spectrum unit? And in sequence, linking with the benefit of acceleration, I give you that acceleration as input. So that means this function of acceleration. Yeah, what should be this value is? You see the expression, right? So acceleration is centimeter per second square, let us see. Then what will be the F omega? That's the silver piece here in the center of the tongue. So this should be able to correct you per second square, right? And then this is second. So therefore it cancels. Then it will be centimeter per second. But there is another term, e to the power I omega t. That part will contribute or not? Yes, no, it says why pass for the local start. But one of the so he's on a point late. But the word that unit is. When the word term is the unit is because this is the omega A is equals to 2 by time. So this is the time multiplied by the time. So there is time many time getting gone. So that would not be. So if you have a centimeter per second square as a input to the things, then you will be getting output. That means the spectrum will be multiplied with the time, right? So if it is a velocity, then you will be getting this displacement. So that means 1 unit of centimeter, right? If it is a displacement, then you will get displacement dot second, right? So that you have to understand, because in case of your MATLAB or any other computing software which will calculate the FFT or something like that, they will not calculate because they do not know what data you are inputting. You might be inputting centimeter per second square. I might be inputting something else, or the micrometer per second or something like that. So they will not take that part. So after that, you have to multiply it with a dt because they will be doing only the Fourier transform of ft, but you have to multiply it with your delta t value, whatever is your time second or microsecond or things, and then that will be giving you actually your Fourier transform value. So the MATLAB is only calculating the Fourier transform of that particular thing. So they will not multiply with a dt. So you have to do that in order to calculate the actual spectral with the proper unit. So that you need to be careful. So this is your and then you can calculate phase spectra with the imaginary part divided by this part. Then that will be the arctan of tan inverse of g with the imaginary part with the g of real part. Then that will be phase spectrum of the data, and then your amplitude spectrum will be equals to the square root of the if I do not take the square root, then that if I just only add these two terms, then that becomes a power spectrum because it's an amplitude square. Amplitude square is always a power, right? So that's that part is fine, right? Now, so there are periodic spectra and there are non-periodic spectra. So that means the periodic spectra means whenever the spectra repeat after a regular interval of time, then we call it as a periodic things. And if it is not, then it's a non-periodic spectrum, right? So your if you try to do these things, so then your ft, if the function is a periodic function, if it is an ft is a periodic function, then the Fourier transform will be equals to fn into e to the power. If I can write it as a Fourier series, then this will be this. I can write it like this way. Then if it is a period, then we can integrate it from minus t by 2 to plus t by 2 with your this part, right? So minus t by 2 to plus t by 2 because we are assuming any function. It should not be a rectangular function. So minus t by 2 to plus t by 2. If it is a periodic function, then we could only integrate up to this much to a ft into e to the power I omega t into dt, and that will be that omega 0 will be 2 t pi by 2 pi. So that is your fundamental frequency, right? So that is the frequency that you are looking for, right? So therefore the ft can be written as a 1 by t into this one. So I can put this fn value here and then e to the power I omega g. So this fn is equals to this much multiplied by dt. So you can do that. And then, so what you need to calculate that the delta omega, this is what, this means what? So the delta t is the time sampling. So that means you are sampling, if you have a time series, if I have a time series, then because actually we are all giving this time series, right? So we are giving the amplitude data at different time, right? And that time is that delta t, right? So that time is that delta t. So what is your delta omega?
We're going to say the power. Anything.
So what is your what is your omega 1? That's the I'm trying to understand. In the frequency domain with us and the self-caterer, so that is in the Fourier transform of it, then you will be getting some sort of a Fourier transform, and then this will be also given as a because they will not give this your analog function. They will be also giving you in a discrete form. So that discrete form will be equals to your delta omega, or you can say it is a delta f, whatever when unit you want, then delta f or delta t. So this delta omega means it's a 2 pi over delta t, right? So delta omega means it's a 2 pi over 2 pi over f, so delta f, and that means this will be the 2 pi over delta t. So therefore 2 pi get cancelled. So delta f will be equals to 1 by of t, right? So 1 by of t. So, so that is your delta f. So if you have given that this much of time of data, so then I know what will be my sampling interval, right? So if I give a very long length of data, then the sampling will be done much more precisely or much more loosely. So that is what I like to know. If you are giving a, say suppose a 20-second worth of data, right? And if you are giving a 50-second worth of data, then what will happen? So where the omega value will be the small and where the omega value will be less? Delta omega value. So one will be the one, let's see, this is your 1 and this is the 2, right? So for the first one, delta f will be equals to how much? 1 by t. T is equals to 20 seconds. And for this, delta f2 will be equals to how much? 1 by
it for your so the weeks still the same fluctuations. Yeah, that we're not sure some but it's what they need to come up. So now it's again what but the splitting high one. Whatever the bit is.
So, dude,
Yeah. Go to 3.3 or do it. And money. This will make that straight. In that I just kept me this up and give up his straight. It's the dot. And my thing. Zero white and spot. And he said, white zero goes. What did it get on it? They have to put so. What can you do when you place your thing as a shin? Shin, well, it. So like feeling the already. Then I can see how that thing making it painter. Apparently, there was something when yes. Yeah. Well, when you something back. But if you ever saw this country where it was some you will get, you know, I better get it. I'm gonna request something like that in when you try and keep careful. Yeah. Next.
So, so if the t becomes larger, delta omega is smaller, right? Or the so that means if you are trying to calculate a very very accurate sampling of the Fourier transform or the spectra, then you have to give a little bit larger length, right? Now, larger length, how can I give a larger length? Because if you have this much of time series, I need a very precise sampling. Then what should I do? I need to know the 50 precise values. If I have a say suppose 50 second, I have a 50-second thing, but I need a very precise number than the 0.02. Then what should I do?
well, we did the nice this again. Not you do that actually, you will take.
Let's squeeze them. Excusing the same sizes.
But now, within me the little. We the window.
We use a English label as like not
I said,
it has the seals on the performance of the things. Like the entire one way game. We need all about it. And it's getting you can get a much more precise
Sampling, right? So that way, this is another way, but there are a lot of other ways you can do that. But the main thing is this, that if you want the coarse sampling, then that whatever you have used, that's fine. But if you want it much more fine sampling, then you have to increase your time series, right? So that the things, and so in case of your if you calculate ft from your f omega, then this is what you call it as a inverse Fourier transform. And if you calculate the ft from the if you calculate omega from your ft values, then this is this one. So this will be the minus, but this will be the plus. Okay, so that part is fine. So we'll be doing this then the next day, or might be the afternoon a little bit, and then we'll do. Okay, thank you.